Our second speaker for the morning session today is Professor Richard Kenyon from Yale University, and he's going to talk to us about dimers and webs. Please go ahead, Richard.
Okay, thank you, and thanks for the invitation, and happy to be here. That was a great talk, Ralph. I'm going to talk about joint work with a postdoc, Dan Douglas at Yale, and a grad student, Howlin Shi. And it's a work in progress, so feel free to interrupt with questions. I appreciate whatever kind of questions or comments you have. All right, oops. So I assume, probably we all know what a dimer cover is. I'm interested in combinatorics and, understanding probability of random dimer covers on a potentially large graph, right, like the grid. And just by itself, one dimer cover you don't see very much, but why do we study dimers? It's because, we can count them. And I suspect that everybody in the audience knows this, but let me go through it just to set the notation here. How do you count, excuse me, dimer covers of a planar graph? In this case, bipartite planar graph. So all my graphs in this talk are going to be bipartite and planar. In this case, we make a matrix, which is called the Castellane matrix. It has, rows indexing the white vertices and columns indexing the black vertices. It's just a signed adjacency matrix. So you put an entry 1 plus or minus 1 if the vertices are adjacent and 0 otherwise. And well, how do you choose the signs? The signs are chosen according to the so-called Castellane rule, which is that around a face, which has if the face has length L, it should have L over 2 plus 1 modulo 2 minus signs on it. For example, if your graph is a square grid, all the faces are square. So each face has to have an odd number of minus signs. And here's an example of a set of signs satisfying the Castellane rule. In some sense, all other choices of signs are equivalent to this one. They're gauge equivalent in a well-defined sense. And the main result of, the reason we study dimers is because there's this very simple result of originally of Castellane and Temperlane-Fisher in the 60s that the determinant of this matrix counts the dimer covers. All right, now I'm interested. Suppose I take this dimer cover of square grid and I put another one on top of it. I overlay 2 dimer covers, the blue and the green one. Then I'm going to call that then you get these loops. Each vertex has now degree 2. You get some doubled edges and some loops. And if you forget the colors, if I forget the fact that one dimer was blue and the other one was green, if I color everything black, then I'm going to call that a double dimer cover. So a double dimer cover is not quite the same thing as a union of 2 dimers. It's not an ordered pair of dimer covers. It's an ordered pair once you forget the coloring. So and let's call that omega sub 2, the set of double dimer covers. And it can be related, of course, the number of ordered pairs of single dimer covers, right, which is the omega 1 squared. It's the sum over double dimer covers of 2 to the number of loops. So it's a model of loops on the graph where every loop gets a factor of 2. Now, we want to study this model for a large planar graph, and what kind of observables do we want to compute? And one thing you might be interested in is suppose that we, puncture some faces of our planar graph, like the one here and the one there, and then I can ask maybe I puncture 10 faces. I'm going to ask, what's the probability of finding a loop or set of loops with a particular homotopy class, isotopy class in the complement of these faces, punctured faces. For example, what's the probability that there's a loop which surrounds both of those? Or what's the probability that there's 3 loops which surround both of these punctures? Right, those are some sort of large scale observables which in principle we would be interested in computing. Okay, any questions so far? All right, so this type of question can be answered using this Castellane matrix, but with an added matrix system, SL2 local system that you put on top of the graph. So even though I'm interested in the sort of basic case where I'm just taking the uniform measure on all dimer covers, I'm going to use an SL2 system to probe the dimer model and determine these probabilities. So what do I mean by SL2 local systems? It just means that for every edge in the graph, for every vertex in the graph, I'm going to put a 2-dimensional vector space, R2, and for every edge, I'm going to have a matrix, a linear map, determinant 1 linear map between the two, SL2 map between the two. Let's call that phi WB from the white. It's orient. You can think of the map, the vertices as oriented from white to black, and then I just associate a matrix to every edge. And if now I have a loop in my double dimer cover, if I have a loop on my graph, then if I have a loop gamma on my graph, I'm going to call phi sub gamma the monodromy of the connection around that loop, by which I mean the composition of the matrices around the graph, or around the loop. And of course, the monodromy is going to depend on the starting point, but the conjugacy class will not depend on the starting point. Furthermore, I'm going to assume that the connection is flat, by which I mean I'm going to have I want to assume that connection is trivial, the trivial monodromy around contractible cycles. So only the only interesting loops are the ones which are topologically non-trivial on the underlying punctured surface. So here's the picture, right? I have a potentially large, complicated graph on a simple surface. Like in this case, it's just a disk with 2 punctures, right? A very fine graph, and then I'm going to put a flat connection, which means a connection which is trivial on all the small faces, but when you go around a puncture, you pick up a non-trivial monodromy. For example, you can just have the connection be supported on this sort of a zipper, a path in the dual graph connecting the puncture to the outer boundary. Okay, now when we superimpose when we take a double dimer configuration, rather, it has a set of loops. Some of those loops will be trivial and some of them will surround the punctures. So, to every loop, I can associate the trace of its monodromy. Of course, the monodromy itself depends on the base point, but the trace doesn't. And not only does the trace not depend on the base point, it doesn't depend on the orientation. Because the matrix is in SL2, the inverse of a SL2 matrix has the same trace as the matrix itself. The inverse of the trace is invariant under inverses. So there's a well-defined quantity associated to each loop called the trace. For example, this loop here, will be just the trace of AB, where A and B are those 2 matrices on the zippers. And so for every double dimer configuration on my graph, M, I can define a quantity which I'm going to call the trace. It's not the trace of any matrix, it's the product of the traces of all the loops that are formed all the loops contained in that double dimer configuration, including the trivial ones. So if I have a trivial loop, its trace is going to be 2 because the trace of the identity matrix is 2. So, if you have a trivial loop, it counts as a factor of 2, but the non-trivial loops will count whatever the trace is of that particular connection. So that defines the trace of any double dimer configuration. And okay. And well, the point is that this trace function now can be used to detect the homotopy type of the loops in the configuration. And here's the theorem, which here's the theorem, about SL2, which is a number of years old. I guess it's 8 years old or so. We can define a Castellane matrix K in the presence of an SL2 local system. So remember, phi is once we choose a basis for the vector space at every vertex, then we can just, phi is just a choice of a matrix on every edge. And we can put those matrices into the Castellane matrix to make a matrix of matrices. In this case, for example, I've got a 2x3 grid. The graph has 3 white vertices and 3 black vertices. It's a 3x3 matrix, but every entry is an element of SL2. Really, it's really well, except for the signs, some of the entries, and also you might have multiple edges, in which case the entries are really just 2x2 matrices, not necessarily in SL2. And given a planar bipartite graph with a SL2 local system on it, we construct this Castellane matrix of matrices. Now that was called K of phi. Now we can make a larger matrix by just removing all the inner parentheses to make, right? Instead of having a 3x3 matrix of 2x2 matrices, I can just think of this as a 6x6 matrix of real numbers, right? That's called K tilde, where I just remove the inner parentheses, and the determinant of K tilde is a state sum. It's a sum over all the double dimer configurations of the trace. And I forgot to put a plus or minus. Well, I guess no, there's no plus or minus in this case. So I wrote the right thing. The determinant of this large matrix is a sum over double dimer configurations of the trace. In particular, as a special case, if I just put the identity connection everywhere, then I will get the usual partition function 2 to the number of loops, right? Because the trace of for the identity connection, all the traces are 2s, powers of 2. Okay. Everybody happy so far? On a Zoom talk, you'll get almost no feedback from the audience. So occasionally, if you're in the audience, do me a favor and say yes or no or something like that. Put your thumb up. Okay.
Can I ask, do you recover Castellane's original theorem in this way, in a way?
Well, we use Castellane's theorem to prove this one, so I don't think we get anything new.
Okay.
Yeah. All right. Right. So here's the. I just rewrote the theorem statement again. But what we can do now is reorder the sum, right? So rather than thinking of this as a sum over double dimer configurations, let's think of it for each finite lamination. By lamination, I mean a finite closed curve system on the surface, lambda. I can look at all the terms here, whose right. If you have 2 double dimer configurations which are isotopic as simple closed curves, then they have the same trace. If you ignore in fact, you can ignore the trivial curves because those just give you factors of 2. But if you don't ignore if you ignore the trivial curves, then you could just look at for each simple closed curve system on the surface. You collect all the double dimer configurations which contribute to that, which have that particular isotopy type, and then we get a coefficient C lambda. So this determinant, once I rearrange the sum, I can write it as a sum over simple laminations, lambda, the trace of lambda, times some coefficient. And that coefficient is like, that's the coefficient which I'm looking for, because that tells me the probability, that coefficient will tell me the probability that if I take a random double dimer configuration, it'll have my desired isotopy type lambda. Right, so now the question is, can we, I mean, of course, the left-hand side we can compute as a determinant of some explicit matrix. Can we compute the C lambda from the left-hand side, right? And it's a theorem, of representation theory of Fock and Gombrov that says that traces of simple laminations, the objects which appear on the right, actually form a basis for the space of regular functions on the representation variety, which means that as you let the flat connection phi vary, you and think of the left-hand side as a function on the representation variety of all flat connections, you can in principle extract all the coefficients here because the traces are linearly independent and in fact form basis for the functions. Oops, let me go back. So the corollary to this Fock-Goncharov theorem is that the coefficients are in fact determined by the left-hand side, which means you can extract, in principle, there's a way to extract them. However, that's a slightly mysterious thing. I don't, except in for some simple surfaces, we don't really know. We don't really have an effective procedure to extract these coefficients, right? We know that they are, I mean, for a large graph, you can, of course, I mean, for any fixed finite graph, you can just look at all possible laminations and just expand everything and find the coefficients. But if you have a sequence of growing graphs, we don't know an effective procedure for extracting these things. So that's kind of an open question. But let me show you some examples, very simple examples. Here's a simple surface, a torus, right? Suppose we have a torus, we put a nice fine grid, maybe a square grid on a torus, take a random double dimer cover, and then I can ask, what's the probability that my random double dimer cover, if I just focus on the topologically non-trivial curves in that double dimer cover, they have some particular homotopy type or homology type. In this case, it's the same. And the theorem, the somewhat non-trivial theorem here, is that the probability that your random double dimer cover has k curves in homology class I, j has a beautiful form. It's the probability proportional to a exponential of a quadratic function of I, k, and jk. So anyway, there's a sort of theta function. The right-hand side is some sort of theta function which describes the homology class of a random double dimer cover, the isotopy class of a random double dimer cover. And this, right, this is in the limit epsilon goes to 0, and this quadratic form only depends on the the conformal structure of the torus. And there's lots of interesting kind of non-trivial mathematics going into this calculation. But it can be done in this case because the torus, can be diagonalized explicitly. There's a calculation one can do. But for more complicated surfaces, I certainly don't know the answer, and that's kind of an interesting, non-trivial open question in scaling limits of dimer models, right? What happens for other surfaces like a genus 2 surface? Okay, so now we're going to move up to the present, and I'm going to take instead of 2 dimer covers, I'm going to take n dimer covers. And for most of the talk, n is going to be 3, just because it's easier to draw those pictures. You can make sense, right? So what I did was I took a blue, a red, and a green, and I just took 3 random dimer covers and I superimposed them. And again, I'm going to ask what kind of structure is there in this union? And one way to detect that structure is to put some punctures in the graph, like at these vertices, and ask, can I somehow tell something topological about the type of this underlying triple dimer cover now, or Enfold dimer cover? So this object, you can call it an Enfold dimer cover. It's also called we call it an N multi-web because it's a generalization of a web. What's a web? It's just a N valent graph. But it's, in what sense is it different from a web? It's because we allow multiplicity. So there's some edges have multiplicity 3, some have multiplicity 2, some have multiplicity 1. Okay, and I'm going to call omega sub n the set of n multi-webs. If you want, you can just take a triple dimer cover and then forget the coloring, or Enfold dimer cover and then forget the coloring. But remember the multiplicities, how many times each edge gets covered. Okay, and let me tell you the main result, and then I'll explain the terms in the main result. The main result is that whatever we did for SL2 extends for SLN. And the theorem is that there is a Castellane matrix, which is just the usual Castellane matrix, which you would define just like the SL2 case. You remove the inner parentheses, and you get some largish matrix. You take its determinant, and the determinant is again the sum over all n webs, n multi-webs of the trace. And so I have to tell you what the trace is. Okay, that'll take a few slides. Okay, right. Let me just remind you, right, that n multi-web is a multi-set of edges with total multiplicity n at each vertex. So to each edge, I associate a multiplicity, and the sum is n at each vertex. Now, I'm going to take an SLN local system on the graph, just like an SL2 system, except I'm going to, they're n by n matrices now. And I'm going to show you how to define, I'm going to show you how to define the trace. And it should satisfy, a couple of simple things. It should be gauge invariant. That is, if I, change the basis at one of my vertices, the trace should not change, and it should generalize the trace for loops. And well, of course, I could have written a bunch down. It should be some, tensorial, has some tensorial definition. So here's the definition. And let me just give the definition for n equals 3 because it's easy to generalize from this case. Now, at each vertex, we have a 3-dimensional vector space, but I'm going to take 3 copies of it, one at each edge, or at each half edge, which connects. So just a minute. I have yeah, sorry. Right, so I realize I gave a special case here, which is when my graph is trivalent. So let's assume that our graph is trivalent first, and then I'll tell you how to extend it for an arbitrary valency graph. So first I'm going to tell you the trace of a web, and then I'll tell you the trace of a multi-web. Okay, so a web is, in this case, a trivalent graph, because we're doing the n equals 3 case. All right, so now at each half edge, you have a copy of the vector space, and I'm just going to label them v1, v2, v3, so you can tell which edge they came from, they're sitting on, right? And at each black vertex, that's at the white vertices. At each black vertex, you have the dual vector space, okay? And let's choose once and for all a basis for R3, E1, E2, and E3. Just so, right? At the end, it's going to be basis invariant, but it's good to, at least for the sake of defining things, to define it first in terms of the basis, right? And now at each white vertex, I've got 3 adjacent vector spaces, right? They're just copies of each other, but there's 3 adjacent vector spaces, one associated to each edge. And I'm going to take the tensor product in the cyclic order. I'm going to remember the order, the cyclic order. And in that tensor product, I'm going to choose a particular vector, which is called the co-determinant. And here's the definition, right? It's defined in terms of the tensor products of the basis vectors. And right, in this case, there's 6 terms, one for each permutation in S3, and with a signature. And the terms are just, E11, E22, E33, and all permutations of those. And well, of course, I can do the same thing at the black vertices, except I'm using the dual basis, the Fs. And these, it's not completely obvious, but these things are invariant under SLN based SL3 in this case base change. And then what's the trace? Well, the trace is just, well, you kind of do the natural thing on each edge. Well, you have a tensor over here, you have a tensor over there. You can apply the parallel transport to transport a vector here over to there, and then contract with the dual vector. And that's kind of what's going on. I don't know if this notation is very useful, but you take the tensor product over all the white vertices, you get a huge tensor product of vectors, a vector in the tensor product of all these v's. You get the tensor product of all the f's, and then you contract it with the parallel transports along the edges, the connection, and that gives you a number. That's kind of a mysterious definition. I mean, it makes perfect sense on some level, but it's very hard to, well, figure out what's going on. Here's a very simple example. Suppose my web is just has 2 vertices and 3 edges, right, with parallel transports A, B, and C on them, as illustrated. So, right, there's only one white vertex, and the co-determinant has the 6 terms here. The co-determinant at the black vertices has the 6 terms. I didn't write them all. I just wrote, 3 of them. And then when you contract these 2 together, I could, for example, contract the first term here with the first term there, and E contracts with F to give the, along the matrix A to give ARR. Here the basis, I labeled the basis R, G, and B because R, G, and B are like colors. I'm going to start talking about colors in a second. So, there's 36 terms, there's 6 terms here, the 6 terms here, you get 36 terms in total. You add them all up together, and somewhat magically, it reduces to the following expression: trace of AB inverse times trace of CB inverse minus, trace of AB inverse C inverse, CB inverse, right? Not obvious where this expression comes from, why you get that expression, but that's the answer. And if you like to write it in a more symmetric way, you take the determinant of XA plus YB, plus ZC, and then you extract the XYZ coefficient from this polynomial in X, Y, and Z. Anyway, so I don't know if this makes it less mysterious or more mysterious, but that's the trace. Here's a somewhat less mysterious definition of the same object. I hope it's less mysterious. This is the one we can work with. It's really the same. I just thinking of it in a different language. And so what we're going to do is write the trace as the sum of colorings. Now, at each vertex, now this is a slightly more general setting, which is for a multi-graph, a multi-web. So each edge now has a multiplicity, and I'm going to set n to be 5 just for this illustration of this picture. I'm going to assign colors to the half edges at each vertex, such that at each vertex all colors are present. In this case, all 5 colors are present here, all 5 colors are present there. And you notice that to each edge I assign a subset of colors, and they partition the set of colors. So 1, 3 go here, 2, 4 they'll go there. This is an edge of multiplicity 2, that's an edge of multiplicity 2, that's an edge of multiplicity 1, that's an edge of multiplicity 0, and so on. Right? So I assign those arbitrarily. To each vertex, I assign some colors to the edges, and then respecting the multiplicities, and then along each edge, I look at the parallel transport, which in this case is a 5 by 5 matrix, and I take the appropriate minor determinant. In this case, I take rows 1 and 3 and columns 2 and 5 of the parallel transport here. That gives me a number on each edge, and I multiply those numbers together and add them up. And that's the proposition. The trace expression from the previous slides can be written as this sum of her colorings. And I forgot to tell you about the sign. Except for the sign, it's just the product of these matrix minors. And what's the sign is when you put the colors around a vertex, there's some order, there's a permutation associated to it. 1, 3, then 2, 4, then 5. A cyclic permutation. And it has a signature. I mean, if n is odd, it has a signature. If n is even, it's you have to know where to start. And that's a little bit of, that's a little bit of a, so you, that gives you an extra sign problem. But once you fix the place to start, then you have a well-defined sign for any coloring, and then the trace is the sum over all possible colorings of this product of matrices. In particular, if the connection is the identity, then all these things are just one, and then you just get a assigned sum of colorings. Okay, so then that's now I'm just putting the theorem back up. Now that you know how to define the trace of an Enfold dimer cover, the determinant is the sum of overall configurations of the trace. And I put a couple notes about the sign. When an n is odd, there's a plus or minus sign in front because it depends on a somewhat artificial ordering of the vertices, right? This matrix, if you like, you have to order the edges and columns in some artificial ways, and that will change the sign. When n is even, there's no such sign ambiguity, but the trace has a sign which depends on where you start the linear order around each vertex. Okay. What are we doing time-wise?
Yeah, you have more than 10 minutes left.
Okay. Are there any questions so far? That's the main result. But you know, what are the applications of this result? I mean, does it really help to do anything? So let me tell you about reduced webs. And again, I'm going to go back to n equals 3 because it's easier to draw the pictures. There are versions for other n, but it's more complicated and we still don't really understand it very well. But when you have a web on a 3 web that is a trivalent graph, and there are certain operations. I mean, with an SL3 local system, and there are certain operations, skein relations that you can do to simplify the web. And for example, if you have this 2 adjacent vertices here, then you can rewrite the web which has these 2 adjacent vertices in terms of either the 2 parallel things or this 2 crossing things. So this skein relation doesn't preserve the planarity of the web, which is kind of a problem for us. But if you're dealing with planar webs, then here are 2 consequences of the boxed skein partition, which preserve planarity. If you have a web and it has a loop like this, 2 parallel edges which form a loop, then you can write it as either you remove the loop or you remove the loop and add a cycle. So and it's a skein relation. So one web gets replaced by a linear combination of 2 webs, 2 planar webs again. And it's not so important for the sake of this talk, but you can make here A, B, C, D are supposed to be the parallel transports, the connection on the graph, and you can apply the skein relation even in the presence of a connection, and it gives you something non-trivial. Same thing here. If you have a planar graph and it's got a square face, a trivalent planar graph and it's got a square face, then you can do this. As a consequence of this one, you can show that you can either write the web using the 2 parallel or 2 vertical, 2 horizontal or 2 vertical things with the appropriate parallel transports as shown. These operations allow you to take your web on a planar graph and simplify it to write it as a linear combination of simpler webs. And if you keep applying those operations until you can't simplify it anymore, you get a reduced web on a surface. I mean, if it's on a surface. What we're going to do is, since we started with the planar graph on a punctured surface, remember back at the beginning, we took our dimer model on a complicated graph on a punctured surface. We're only going to apply these operations to topologically trivial faces. So for the purposes of this talk, you can ignore all the labels here and just remember the topology of how. So we're only going to apply this scaling relations when we have a square face with topologically trivial square face where the monodromy is trivial. So in that case, right, we start with a multi-web on a surface with a flat connection. We can rewrite it using these scaling reductions as a sum of reduced webs. Where what does it mean for a web to be reduced? It means you can't simplify it further using scaling relations. That means that every face, there's no square faces. There's no faces of degree 4 or 2 because those you could reduce. So every face has degree 6 or more, then that's called a non-elliptic web or reduced web. Oops. And so you start with your somewhat complicated web like I showed before. You apply these reductions and eventually you get a linear combination of non-elliptic webs which only have, their topologically trivial faces have degree 6 or more, have valency 6 or more. Unfortunately, unlike in the SL2 case, this forget it. That's not what I meant to say. Even though you can reduce any web to a linear combination of non-elliptic webs, there's no obvious canonical way to do it. That is, if you do things in a different order, you'll arrive at a different linear combination of webs, which feels problematic. However, the isotopy types of those webs are invariant. That is, if you do the reduction in a different order, I should have given you a picture to show you that you get different webs if you do things in a different way. But trust me, if you do the reduction, depending on the order in which you do the reductions, you get different right-hand sides, but the number of terms on the right-hand side is always the same. I mean, counted with multiplicity, and the topological types are the same. And consequently, this determinant, which we computed, can indeed be written. You can collect the terms here instead of writing it as a sum over n-fold dimer covers, or 3-fold dimer covers at least. You can collect the terms into their isotopy classes of reduced webs, which I'm calling lambda 3. And so the theorem is that the determinant can indeed be written as a sum over isotopy classes of reduced webs of some coefficient, and the coefficients can indeed then be extracted by some, well, we don't know how, that's still an open question, from the determinant. Okay. So I'm just going to show you how this works in practice in a couple small examples, because we don't know how to do it in general, but for simple surfaces we can do it. And the simplest kind of surface is an annulus, or if you like, a punctured disk, right? Disk with one puncture. If I start with a potentially complicated graph with puncturing only one face and a flat connection there, then I can reduce it to a union of reduced webs. What's a reduced web look like on a once punctured disk? It's just a loop, and it can have either orientation, clockwise or counterclockwise. So what you do is you take any 3 multi-web, any triple dimer cover, you apply the scaling relations, and you eventually get a union of topologically non-trivial oriented loops. Which is kind of it's kind of a boring case, right? But that's okay because there's only one puncture. But as a consequence, the determinant can be written, right? Each loop, if the monodromy going around the annulus is A, then each loop contributes either trace of A or trace of A inverse, depending on the orientation. And those, because we're in SL3, those can be, algebraically independent quantities. All right, so the next interesting case is also already quite interesting, which is the pair of pants. Right? It's a twice punctured disk, if you like. right? On a pair of pants, what does a reduced web look like? Well, you can certainly, get loop components just like before, which are topologically non-trivial on the pair of pants. But there's also components kind of like the one illustrated here. Here, this is, if you look at the black graph on this pair of pants, you see that all the faces are, all the topologically trivial faces are hexagon, are order 6. So this is a reduced web, and all the vertices are degree 3. And every reduced web, in fact, comes from this construction where you take the honeycomb graph in the plane, and you take a rhombus like this centered at the faces of an equilateral rhombus. I mean, a 60-degree rhombus centered at the faces, and you cut it out and you fold this arrow to that arrow, and the double arrow to the double arrow. You get and then you puncture the 3 corners. So that the black graph here that you see here is sort of unfolded onto this pair of pants over here. And so and those are, in fact, every possible reduced component for the multi-web there on a pair of pants. And so the question now is, I have some potentially complicated graph on my pair of pants. Can I extract the coefficient of each one of these special reduced webs? And well, in principle, we can, and we can do it for when the one graph is simple, but not yet for the more general graph. So that's where we are currently. We're still working on it, and that's the end of my talk. Thank you.
Thank you very much, Richard, for the very interesting talk. Thank you. Are there any questions in the audience?